So for the last part of chapter 5, we're going to talk about kinetics, how fast reactions occur, and equilibrium. So the definition of kinetics, it is a branch of science that deals with the rate or speed of chemical change. Here is an exothermic reaction. So we're focusing on hydrogen gas reacting with iodine gas, forming hydrogen iodide gas. Also, what is produced is heat. So this is one of the ways you'll recognize an exothermic reaction is you'll see heat written on the right side of the arrow, meaning heat is produced. Heat is exiting. So if you remember, exothermic is heat is exiting. This diagram right here is what we call an energy diagram. So you might want to write that in your notes, because if I were to ask you to draw and label an energy diagram, this is what one would look like. So a couple things about this diagram. The x-axis has what's called just the reaction progress. So it's kind of as if, at the beginning it's time equals 0 and then time, continues. So, and then along our y-axis we have energy. This particular diagram doesn't have any tick marks here, so it's not giving us any exact energies. It's just going to have relative energies at this point. But it does represent, in real life, a particular amount of energy. So what this is saying is that here at the very beginning, the reactant molecules have a certain amount of potential energy stored in the bonds. Okay? And then as the reaction progresses, it increases in energy, and then as it moves on to products, the products are going to have lower energy than the reactants. So why do the products have lower energy than the reactants? Because they've given up some of their energy to the environment. So the products will have less potential energy stored in the bonds than the reactants. A couple other things here. This is what we call the difference between the energy of the reactants and the energy of the products is what we call the heat of the reaction, or the energy of the reaction, and that is just the difference between how much energy the reactants had and how much energy the products have. So that is an example of an exothermic reaction diagram. So for exothermic reactions, the reactants have more energy than the products. As a result, as the reaction occurs, excess energy is released to the surroundings, so heat is produced. So to explain why there was a hump in that energy diagram, we must include mechanisms of chemical change with our discussion. So I'm going to kind of digress and go through some mechanisms. A mechanism describes what's happening as the reactions are changing into products. So some of these mechanisms are going to talk about how the reactants come together, how or what bonds are broken, and how and what new bonds are being formed. So most mechanisms show how the reactants come together. So these collisions may lead to a chemical change. So for a reaction to happen, the reactant molecules must collide with each other. Otherwise, there's never going to be a reaction between those two reactants. Sometimes, however, that the collision doesn't actually lead to the products being formed, and that's why I have may being underlined. There's a couple criteria that need to happen. So for a collision to be what we call an effective collision, the reactant molecules must bump into each other, they must collide, but they must collide with enough energy to react, and they must also collide with the right proper orientation. Okay. So I have a diagram to help us with that. So this is a picture of the reaction I just had showed you on the previous slide of hydrogen gas reacting with iodine. And this is the producing the two hydrogen iodide molecules. So for this reaction to happen, the hydrogen molecule and the iodine molecule must collide with each other. And they must collide side to side like they're doing here. If they collide head to head, a reaction's not going to occur. So the hydrogen and the iodine collide, and we end up producing these products. Now, what we call that intermediate step, where you're like halfway in between, where you're starting to form the new hydrogen iodine bonds and you're starting to weaken and break the hydrogen bonds or the iodine bonds, that is what we call an activated complex. Another word for the activated complex, we can just write it here on this slide, just in case I use this word, is called the transition state. So in the transition state or the activated complex, you're like halfway between the reactants and the products. So it turns out that the energy content of that activated complex, that molecule, that intermediate molecule, is always higher in energy than the reactants, okay, or the products. Therefore, you always get this hump. So if we were to label this diagram right here at the tip of this hill, so let me flip over my pen. Right here is the energy of the activated complex. Activated, ED. The activated complex. Okay, so technically if we talk about how much energy the activated complex has, we'd come over here to the y-axis and read the y-axis. This is how much energy the reactants have, and down here somewhere is how much energy the products have, because you'd carry it over. Okay, so the activated complex is always higher in energy than the reactants or the products, so you're always going to have this hump. This hump can kind of explain why a match is needed to get a paper to burn. So if paper is combustible, the question would be, well, why doesn't just paper spontaneously combust? Why do we even need a match? Well, it's because you need to give a reaction the activated energy. So that's why this slide is titled the activation energy. It's the energy that's needed to get the reaction to occur. It's really the energy that's needed to form that activated complex. Once the activated complex is formed, then the reaction can quickly go on to products. Okay? So if you were to label how much energy it takes to make that activated complex, or what is the activation energy, that would always be the distance from the reactants to the top of the hump. Okay, so you might want to record that in your notes. The activation energy is the distance from the reactants energy to the activated complex energy. And then the distance from the reactants energy down to the product's energy is what we call the heat of the reaction. And this distance right here is the activation energy. So activation energy is the minimum energy needed to be added to the reactants for the reaction to occur. So right there I'm showing you, this is the symbol we give for activation energy, capital E with that lowercase ACT. And once again, this is an exothermic reaction. We know that because the energy of the products is lower than the energy of the reactants. So as the activation energy increases, so another way to think of that here is as the hump increases, the rate is going to decrease because fewer reactants will have the sufficient energy to get over that activation barrier. So you can usually tell from an energy diagram when reactions are slow or fast by the size of the hump. So if I make the hump bigger, then we would say that that is a slower reaction. The lower the energy hump, the faster the reaction is going to be. So if the previous diagram represented a fast exothermic reaction, then how would a slow exothermic reaction look? So I kind of answered that question for you. You would still have your y-axis, which we would label energy, and the x-axis would be the reaction. That's our abbreviation for reaction process. We want it to be, so you can start anywhere you want. It's kind of arbitrary if we're not going to have tick marks along the Y. So I'm just going to start up here because it tells me that it's exothermic. So I'm going to just pick an arbitrary point to start, and I know that my ending point better be lower because in an exothermic reaction the products have to be lower than the reactants. And then I'm just going to draw a hump. But this one wants me to do a slow reaction. So I'm going to do a very big hump and come down here lower. I need the activation energy to be very high to be a slow reaction. So there are 5 factors we're going to talk about that influence the rate of a reaction. One of them is concentration, then temperature, the activation energy, which we just talked a little bit about. Catalysts will affect the rate of a reaction, and surface area affects the rate. So here's the reaction we're going to look at first. I have some data for you. We're going to talk about this iodine the iodide ion reacting with this persulfate ion. And so I have some data. Now, we haven't talked about concentrations yet. Pretty soon I'm going to be teaching you that when you've got brackets around a formula, that indicates that your concentration is being measured in molarity. But we'll talk about that more in a future chapter. So right now, you go ahead and you do this reaction, and you get your iodine that has a concentration of 0.8 molarity, and your persulfate is 0.8. So you have equal concentrations of the two reactants. And the temperature is about 20 degrees Celsius, and you time this reaction, and you find that it takes 44 seconds. And then you do this little mathematical equation where you take 1,000 and you divide it by the time so that you can get a kind of a relative rate. That's going to help us compare the rates of the other trials. So your first trial, equal concentrations, and it takes 44 seconds for the reaction to occur. Then you go and you do a second trial, and the difference here is you have cut the persulfate ion in half, so you do not have as much of the persulfate ion. And what happens? You keep the temperature constant. Find my pen. And now if you notice, it takes twice as long for this reaction to happen. So the rate has been decreased by half. So what you can infer from that is that if you decrease the concentration, then the reaction is going to take longer. So decrease the concentration, you decrease the rate of the reaction. Here in trial 3, it looks like they decreased the concentration of the iodine this time and kept the temperature constant, and you can see that once again the reaction took twice as long. If we're looking at trial 4, they have kept the concentrations the same between trial 3 and trial 4. So they're holding the concentration constant at this point, and what they're changing is the temperature. They want to see what would happen if we run this experiment at a higher temperature. So they run it at 30 degrees Celsius, and if you notice what happens to the rate between trial 3 and trial 4. Trial 4 occurs at a much faster time, which means a slower time. It doesn't take as long for the reaction to happen, which means it's happening at a faster rate. So what we can infer from this data is that if you increase the temperature, you are going to increase the rate of the reaction. It's going to happen quicker. So I've left you some blanks on this slide so you can add the missing word. As the concentration of the reactants increases, what happens to the rate? And I'm hoping you can see that the rate is also going to increase. Now, I don't only want you to know the relationship there, that if one increases, the other increases. I want you to be able to explain to me why. So the reason, if you have a higher concentration of your reactants, then there's more chances that they're going to bump into each other. So you increase the concentration, you increase the rate because you are increasing the number of collisions. If we increase the temperature, what happens to the rate? Well, once again, that is an increase also. Increasing the temperature increases the rate. But you're going to need to be able to explain to me why. So if you think about it, when you increase the temperature, you are giving the molecules more kinetic energy. They're moving around faster, so they're actually going to collide more often because they're moving more faster. So you're going to get more collisions, but you're also going to get more effective collisions where they're bumping into each other with enough energy to get over that activation barrier. This is why we lower the temperature to keep our foods from spoiling. So we often put our food in the refrigerator because then it keeps it at a lower temperature. So that's going to slow down the rate of spoiling. So increase the temperature, increase the rate, decrease the temperature, decrease the rate. Okay, so that was kind of talking about concentration and temperature. I want to move on to catalysts real quick. So a catalyst is going to increase the rate of a reaction. So if you add a catalyst, it's going to go faster. What a catalyst does is it lowers the activation energy. So if we look at this diagram, the green was the activation energy of the original reaction. So it used to take the reaction before you put the catalyst in. You needed this much energy to get the reaction to start. If you put a catalyst in, a catalyst lowers that activation barrier. It lowers the activation energy needed for the reaction to happen. So you can imagine that the molecules don't need as much energy when they bump into each other. So you're going to get more of those reactant molecules going on to become products. Another thing I want you to know about catalysts is that they're not used up during the reaction. So You start off with your reactants, you add a catalyst, and those reactants turn into products, and then you're left with your catalyst. So then you can capture it and reuse the catalyst. So catalysts are going to increase the rate because they have found an alternative mechanism with a lower activation energy that's available. In our bodies, you're going to learn when you go on to biology and anatomy and physiology and they start teaching you about enzymes. Well, enzymes are just biological catalysts. The purpose of an enzyme is to help a particular reaction occur quicker. The last category that I'm just going to barely touch on is surface area. And this one's kind of intuitive. So for a heterogeneous reaction, what that means is you have two different states of matter. So for a reaction where you're going to have, say, for example, a metal surface, and it's going to react with a liquid. So the liquid's going to come in contact with the metal and the reaction's going to occur. Well, hopefully it makes sense that if you have more surface area, that's going to make the reaction go faster because you have more areas that the liquid molecules can land and react with the solid surface. So increase the surface area, you're going to increase the speed of the reaction. So here is a learning check. State the effect of each on the rate of the reaction. So I want you to read A and tell me whether you think that's going to increase the rate of the reaction, decrease it, or have no change. So if we increase the temperature, what does that do to the rate? Well, that is going to increase the rate. If we remove some of the reactants, well, now I don't have as many reactant particles, so what's that going to do to the number of collisions? You're not going to have as many collisions. So if you remove some of the reactants, you're going to decrease the rate. If you add a catalyst, that's going to increase. You also need to be able to explain to me why. So adding a catalyst is going to increase the rate because it's going to lower the activation energy. What if you place the reaction flask in ice? Well, what that's saying you do is you're decreasing the temperature. So if you decrease the temperature, you are going to decrease the rate. The reaction is going to happen slower. Explain to me why. Well, if you decrease the temperature, the molecules are moving around slower, so you're not going to have as many collisions. When you do have a collision, they're not going to bump into each other with lots of energy because they're moving slower. They don't have as much kinetic energy. E says you increase the concentration of one of the reactants. Well, if you increase the concentration, you're going to increase the rate because you're going to have more collisions. Okay, the last category we're going to talk about here in Chapter 5 is equilibrium. Equilibrium deals with reversible reactions. Up till this point, we have only talked about reactions going in the forward direction. All you have seen between the reactants and the products is an arrow pointing to the right. When we start talking about equilibrium, where you have the reactions happening in both directions, we start using this two arrow system, where one arrow is going to the right and one arrow is going back. So equilibrium represents this reversible change. So what I have is I have nitrogen dioxide turning into dinitrogen tetraoxide and producing heat. But then I also have, at the same rate, the dinitrogen tetraoxide breaking apart and turning into nitrogen dioxide. So both of these are happening in your reaction vessel at the same time. So the definition of equilibrium, it is a condition attained where the rate of the reaction in the forward direction, I'm going to move my pen off the way. Okay, a condition attained where the rate of the reaction in the forward direction equals the rate of the reaction in the reverse direction. So have you ever wondered if all of the rivers are flowing into the ocean? So all the rivers on the continents are flowing into the ocean. Why is it that the level of the oceans are not rising? And I know this is an oversimplification, but basically the rate of evaporation from the ocean is equal to the rate of the inflow of water. So if the rate of evaporation equals the rate that the water is flowing in, then the sea level is going to stay approximately the same. So a chemical reaction that is at equilibrium, it looks static. You might just be looking at your beaker and it doesn't look like anything's going on, but really it's very dynamic. You have the reactants turning into products at the same time the products are turning back into reactants. A reaction that is at equilibrium has both the reactants and products present at the same time. Doesn't mean they have to be in equal concentrations, but you have them both present. So that's hard for a lot of students to conceptualize. You've got yourself this beaker, and both the reactants and the product molecules are floating around at the same time. Okay, so you want to kind of stop thinking about starting off with the reactants and then all of those reactants turn into products. That's what we think about when we have a arrow just pointing to the right. When I tell you that your system has reached equilibrium, that means that the reaction originally went to the right, but at some point you've made enough product molecules that the product molecules start breaking back up into reactants. And equilibrium is reached when the rates of both of those are equal to each other. So here is a generic reaction. HA is our symbol for an acid. So I have this generic acid, and I'm telling you that the color of this acid is yellow. And this acid will break up into a hydrogen ion and then this generic anion. That'll have a negative charge because it lost this hydrogen ion with its positive charge. Well, the hydrogen ion I'm telling you is colorless, but this anion has a blue color. Okay? So at the very beginning, when I take out some of this acid, if I just have this acid at the very beginning, it might just be yellow. And then it's going to start breaking down. It's going to start making these blue molecules. And then at some point, the blue molecules are going to start bumping into the colorless hydrogen ions, and they're going to start making yellow molecules. So when equilibrium is reached, you're going to have the yellow molecules breaking up into blue molecules. At the same time, the blue molecules are breaking up into yellow molecules. So what you're going to be seeing is kind of a green color because you have both the yellow and the blue molecules present. Because remember, at equilibrium, you have both the reactants and the products present in your reaction vessel. So this diagram right here is going to help us out with shifting from one side to the other when we've got a system at equilibrium. So right now what I want you to visualize is that both of my liquid levels are equal to each other. Okay? And I want you to tell me this question here, if this equilibrium shifts to the right, so we are shifting to the right where my acid here is breaking up more to make the hydrogen ion and the anion. So if I shift to the right, what is the effect on the concentration of the hydrogen ion, the anion, and the HA? So I want you to visualize this aquarium where this water here on the left moves to the right. What is going to happen to the level of the HA? And I hope that you say, well, some of this water is going to decrease, so it's going to maybe end up being here. And if I have this moving to the right, then the amount of this is going to increase. Okay? So to answer this then, what is the effect on the concentration of the hydrogen ion? It is going to increase if we shift to the right. The anion is going to increase if we shift to the right because I made more of this stuff over here on the right side. But my HA molecule is actually going to decrease because I've moved less of it. It has broken up into the HA and the H minus. Okay? So one last question here. What's going to happen to the color of the solution if we started off green? So remember at the very beginning we had a certain amount of yellow molecules and the blue molecules, and so what our eyes saw was a green color. If it shifted to the right where I am making more of the blue anion and more of this colorless hydrogen ion, and we said that our yellow molecules decrease, what happens to the color then of the solution you're looking at? Now it's not going to turn completely blue. We're going to say that it's going to like turn bluer or less yellow, or maybe it might turn more like a forest green or something. So when you're shifting an equation at equilibrium, you're not ever going to go 100% to one side. Okay? So the colors are going to become more of one color and less of the other depending upon which way you shift. So there is a principle called the Chatelier's principle, and it states that if a stress is applied to a system at equilibrium, so you have a reaction at equilibrium, going the same rate in the forward direction as you are in the reverse direction, and you put a stress on that system, then a change is going to take place that's going to relieve the effects of that stress. So here are a couple examples of what I mean by a stress. If you change the concentration, that's a stress. Change the temperature, or you change the pressure. So the way we normally change the pressure on a system is by changing its volume, which we'll talk about that more. In this course, we're only going to be concerned with concentration and temperature stresses. Okay, so we're not going to talk about how changing the pressure is going to affect the equilibrium, but we will change the concentration and change the temperature. One other point to notice is that a catalyst is going to have no effect on a system at equilibrium. Okay, so it might speed up the reaction at the very beginning. So at time equals 0, when all you have is the reactants, a catalyst might help you reach equilibrium quicker. But once you're at equilibrium, the catalyst isn't going to help. Okay, so don't be confused by that. The previous part, when I started off this lecture, we talked about the rates of reaction. And if you look back in your notes, you're going to see that when I was talking about the rates of reaction, we just had one arrow pointing to the right. Okay, a catalyst will speed up the rate of a reaction. But once you've reached equilibrium, then a catalyst is going to have no effect. So make sure you read those test questions carefully. So let's focus on some of our stresses. So let's say we're going to stress our system at equilibrium by doing a concentration stress. So let's first, look at this equation we're going to focus on. I've got nitrogen gas reacting with hydrogen gas to produce ammonia. And when the ammonia is produced, it's also producing heat. So hopefully you could say, if I was to ask you if this was an endothermic reaction or an exothermic, I would hope that you would say exothermic because heat is on the product side. Okay? So if I change the concentration, so let's read this. If the reaction is at equilibrium and we add more nitrogen, so we're going to increase the concentration of the nitrogen, how will the system respond? So the problem is that we have just dumped in some more nitrogen, which is a stress. We have too much nitrogen. So according to Le Chatelier's principle, this equilibrium needs to react in such a way that it's going to counteract that stress. So it needs to figure out a way to use up nitrogen. Well, you tell me, if I am moving to the right, if I focus on the forward direction here, where my nitrogen and my hydrogen are turning into ammonia, and then if I focus on the reverse direction where ammonia is breaking up or decomposing into nitrogen or hydrogen, which one of those directions is going to counteract the fact that I have just dumped in some more nitrogen? Okay? If you told me that the way this equilibrium is going to shift is that it's going to react by shifting to the left, I'm going to tell you no. Shifting to the left is ammonia breaking up, making more nitrogen. That's just compounding the problem. The stress that I gave the system was I increased the concentration of nitrogen. So ammonia is not going to want to break down and make more nitrogen and hydrogen because that's just going to compact the problem. So what's going to happen is this reaction is actually going to shift to the right, because in shifting to the right, my reactants decrease and my products increase. So that's going to counteract the fact that I have increased the amount of nitrogen. So if the reaction's at equilibrium and we add more nitrogen, how will this system respond? I'm giving you the solution to these few questions because when we have a lab where we do a lab on Le Chatelier's principle, and I want you to be able to, in the lab, I expect you to be able to kind of think on the molecular level and to explain to me what concentrations are increasing and decreasing. So I've put on some of the verbiage we use so that to kind of help you out with the lab. So additional nitrogen. So my stress was I have the system at equilibrium and we increase the amount of nitrogen. So additional nitrogen is going to cause a concentration stress. The problem is we have too much nitrogen. So the only way that this system can reduce the amount of nitrogen is to combine it with hydrogen. Thus, as a result, more ammonia and heat are going to be produced. Since more products have been formed as a result of this stress, we say that the equilibrium has shifted to the right. So by increasing the concentration of the nitrogen, that causes this equilibrium to shift to the right, producing more ammonia and heat, and decreasing the amount of nitrogen and hydrogen. So there's two ways to stress a system that's at equilibrium. You can either have too much or too little of something. Okay, so our last example, we increased the concentration of nitrogen, so we had too much nitrogen. How would this reaction react, or what would be the effect on this equilibrium if we removed hydrogen? So now our stress is going to be too little hydrogen. Okay, so try to pause the video and think through this. If my problem is too little hydrogen, which way will this reaction shift in order to produce more hydrogen? So reducing the hydrogen will cause a concentration stress. Too little or not enough hydrogen, the only way the system can replace the amount of hydrogen is to decompose the ammonia. So as a result, more nitrogen and hydrogen is going to be produced, and heat is going to be used up. So we say that that is a shift to the left because we're decomposing the ammonia and producing more nitrogen and hydrogen. So the heat's going to be used up as this reaction shifts to the left. Since more reactants have been formed as a result of this stress, we say the equilibrium has shifted left. Okay, so just to summarize that for a second, if you increase the reactants, the equilibrium is going to want to use up the reactants, and the way it does that is to shift to the right. If you decrease the reactants, it's going to shift to the left to try to make more. So what you're going to notice is it's always going to be that the equilibrium is going to shift away from an increase or towards a decrease. So, and it's going to be the same trend that we're going to see with temperature. So let's look at the equation we've been dealing with. If the reaction's at equilibrium and we add heat, so we're going to increase the heat, how will the system respond? So additional heat is going to cause a temperature stress, meaning we have, in this case, we have too much heat. The only way the system can reduce the amount of heat is to use it to decompose the ammonia. Thus, as a result, more nitrogen and hydrogen is going to be produced. And because we are getting more reactants, we are going to say that the equilibrium shifted left. So increasing the heat caused the equilibrium to shift left. So remember what I said before, it shifts away from an increase or towards a decrease. If this reaction is at equilibrium and we remove heat by cooling, how will it respond? So now we're going to decrease the heat. Remember, it shifts away from an increase or towards a decrease. So in this case, it's going to shift to the right because it's shifting towards a decrease. But in terms of the molecular level, to explain this a little bit more deeply, the stress was too little heat. Let me go ahead and get to this slide. Okay, we decreased the heat. So reducing the heat causes a temperature stress, not enough heat. The only way the system can produce heat is to react more of the nitrogen and hydrogen and make ammonia and make more heat. So we stressed it out by removing the heat. It says, oh my goodness, I need to make more heat. So when I know that when nitrogen and hydrogen combine, I make ammonia and I make more heat. So shifting to the right is going to be what happens if I remove the heat. But remember I said, the equilibrium shifts away from increase and towards a decrease. So since more products have been formed, we say that the equilibrium has shifted right. So here's a learning check. How would this analysis change if the reaction were endothermic? So I flipped this reaction around. So now I have the ammonia and heat on the left side, producing nitrogen and hydrogen gas on the right. So we would know this is endothermic because heat is on the left side. If the reaction is at equilibrium and we remove heat by cooling, how will the system respond? So I'm going to decrease the heat, and you would say that you need to be able to tell me which way the reaction is going to shift. It's going to shift in a way that's going to produce more heat. So the question to you is, if I shift to the right, does that produce more heat? Or if I shift to the left, does it produce more heat? Well, if I'm shifting to the right, it's going to produce more of whatever's to the right of the arrow. If I'm shifting to the left, it's going to produce more of what's to the left of the arrow. So let's focus on my arrow pointing to the right. If you say it's going to shift to the right, that's going to produce more nitrogen and hydrogen. Well, that's not what we want. We decrease the heat. So Le Chatelier's principle says it's going to shift in a way that's going to counteract the stress. So it needs to produce more heat. So shifting left is the correct answer, because if it shifts left, it's going to produce more of what is there on the left side. So use the following equilibria to explain why chicken egg shells are thinner when chickens are overheated. And here's a hint. Chickens don't sweat to cool themselves like we do. They pant, which decreases the amount of carbon dioxide in their system. So let's look at this for a second. This calcium carbonate solid is the eggshells. And we have all these systems at equilibrium happening inside the chicken's body. Okay, so when the chicken starts to pant, that causes the carbon dioxide levels to decrease inside the chicken. So if we look at this very first equilibrium that's happening, where carbon dioxide and water makes carbonic acid at the same rate carbonic acid is making carbon dioxide and water. If I stress the system by decreasing the carbon dioxide, this first equilibrium is going to shift which way? And hopefully you said it's going to shift left because it wants to make more carbon dioxide. Well, when it shifts left, that is creating more carbon dioxide, but it's also decreasing the amount of carbonic acid. So the carbonic acid concentration is going to decrease because this reaction is moving left. Well, let's move to our next equation then. That's if I said that the carbonic acid's decreasing, so I'm going to put a decreasing here. Which way is this equilibrium now going to be forced to shift because I decreases the carbonic acid? Hopefully you say it's going to shift left because it's going to try to make more carbonic acid. And that's going to cause my hydrogen carbonate ion concentration to decrease. So if I look at this next equation, hydrogen carbonate ion decreased. So this reaction shifts left in an attempt to make more of it, which is going to cause my carbonate ion concentration to decrease as it shifts left. So if the carbonate ion decreases, that's going to cause this equilibrium to shift left in an attempt to make more carbonate ion. And so that means I don't have as much calcium carbonate around for the eggshells. So when chickens are overheated, they start to pant, carbon dioxide levels decrease, which cause the amount of calcium carbonate in their bodies to decrease, so they don't have as much to produce the eggshells. So your chickens end up having thinner eggshells. Isn't that kind of cool?